Hi everyone, today I'm going to evaluate the performance of three upwind schemes with different orders of accuracy under strong convection using the normalized variable diagram. In this presentation, first I'm going to answer the question that what is a strong convection? After that, the normalized variable diagram is presented. Next, I talk about the modeling of the convected control volume phase value using the upwind schemes, including the first order upwind scheme, second order upwind scheme, and third order upwind scheme, which is also called the quick method. And finally, the performance of the upwind schemes under strong convection is evaluated using the normalized variable diagram. One big challenge in CFD is the successful modeling of strong convection. However, what is a strong convection? To explain this, I'm going to give you an example which involves the modeling of the free surface between water and air. In this regard, the volume of fluid method, which is famously referred to as the VOF method, is used in many commercial CFD codes to model the free surface between the water and air. The VOF uses the fraction of the cell occupied by water indicated by alpha underscore I to locate the free surface. The alpha underscore I is defined as this equation where V underscore I is the volume of water in the cell and V is the volume of the cell as shown in the following figure. So here alpha underscore I is called the water volume fraction. To have a better understanding of the water volume fraction values, this figure here shows the water free surface together with the values of alpha representing the volume fraction of water in each cell. In this regard, the value of alpha equal to 1 indicates the cells filled with water, as can be seen here, right? Equal to 0 indicates the cells filled with air, right, as can be seen here. And cells where the value of alpha lays in a range from 0 to 1 contain the free surface, right, as we can see here. As can be inferred from this figure, on the free surface there is a strong variation in the water volume fraction value, which changes from 1 in water to immediately 0 in air. This abrupt change of water volume fraction is a good and practical example of a strong convection, which is associated with step-like profiles of variables. Later in another video, I'm going to explain further the modeling of the free surface using the VOF method. But for now, we are going to evaluate the performance of upwind schemes in modeling a strong convection. The upwind schemes that we are going to evaluate include the first order scheme, second order scheme, and third order scheme, which is also referred to as the quick scheme. For this purpose, we're going to use the normalized variable diagram. Now let's see what is the normalized variable diagram. The normalized variable diagram is a plot which describes the locally normalized convected control volume phase variable with respect to the normalized adjacent upstream node variable. To explain further, consider the variation of a convected scalar variable phi, as shown here, which is a function of x, y, and z, along a direction normal to a control volume phase f, as shown in this figure. Okay, here d stands for downstream, C stands for central, and U upstream. F is of course the cell phase that we are going to talk about it. Okay, note that the labeling of node values downstream, central, and upstream depends on the normal velocity direction as is indicated here, right? As of course does the choice of node for phi underscore u. Let's define now the locally normalized variable phi as follows. Okay, using this normalized variable, this figure here in terms of the normalized variable can be plotted as follows. Okay, what is important here is that in terms of normalized variable, the value of phi, right, the value of the variable phi at upstream is equal to 0, and in the downstream is equal to 1. Therefore, based on this figure, and as we will see later in this video, the normalized variable diagram describes the normalized convected control volume phase value at phase F, right, with respect to the normalized adjacent upstream node value at C. Okay, using this diagram, it becomes easy to realize when a scheme is both accurate and monotonic. Now let's talk about the modeling of the convected control volume phase value using the Upwind schemes. Consider the convected scalar phi again here, okay, along a direction normal to a control volume phase F as shown in this figure. Okay, the first order upwind scheme approximates the phase value of phi by its value at the node upstream as shown here in this equation, where H in fact it denotes higher order terms. The first order upwind only uses the first term, which is here, right? The main advantages are that it is easy to implement and that it results in very stable calculations, but it is also artificially very diffusive. This can be inferred from its leading truncation error term as shown here, okay, which is diffusive. In other words, it resembles the diffusion term. This numerical diffusion gets larger in multi-dimensional problems if the flow is oblique to the grid. The truncation error then produces diffusion in the direction normal to the flow as well as in the streamwise direction, which is a particularly serious type of error. On a uniform grid, the second order upwind scheme uses the values of phi at two upstream points as shown in this equation. As can be observed, its leading truncation error term is quadratic. This scheme is more accurate than the first order upwind scheme, but in regions with strong gradients it can result in phase values that are outside of the range of cell values. In other words, it is subject to produce overshoots. So it is necessary to apply limiters to the predicted phase values when we use this particular scheme. Okay, now let's talk about the third order upwind scheme, which is also referred to as quick, which utilizes the values of phi in two adjacent nodes of D and C together with that at the next upstream node U as shown in this equation here. The first three terms on the right hand side represent the quick approximation, while the fourth term is the principal truncation error, which is cubic. The quick scheme has several attractive properties such as no numerical diffusion, as the leading truncation error is third order, inherent convective stability as it uses the upwind curvature terms, and it is computationally efficient. The only shortcoming of quick scheme is its tendency to oscillations under strong convective conditions. Okay, so let's now evaluate the performance of the upwind schemes under strong convection using the normalized variable diagram. As I mentioned earlier, to evaluate the monotonicity and accuracy of these schemes, we are going to use the normalized variable diagram, a plot which describes the locally normalized convected control volume phase value with respect to the normalized adjacent upstream node value as shown in this figure. For first order upwind scheme, the normalized phase value is equal to the normalized adjacent upstream node value, right, as shown in this equation here. For second order upwind scheme, we again have a linear relation between the normalized phase value and the normalized adjacent upstream node value, but with a different slope, okay, as shown in this equation here, right? And finally, for quick or the third order upwind scheme, of course on a uniform grid, the normalized convected control volume phase value is written like this, okay, based on these equations, and as can be expected, the normalized phase value is only a function of the normalized adjacent upstream node value. Okay, the normalized phase values obtained from first order, second order, and third order upwind schemes are shown in the following plot as a function of normalized adjacent upstream node value. Okay, here we have the normalized phase value, and here we have a normalized adjacent upstream node value. This plot, in fact, is the so-called normalized variable diagram. Both the second order and third order upwind schemes pass through the point 0.5 and 0.75 labeled as Q, right? The first order upwind scheme passes through the origin O and point P at 1 and 1, okay? As shown by Lannert, 1988, any scheme to be second order accurate must pass through Q. Additionally, any scheme to be third order accurate must pass through Q with a slope of 0.75. Lannert 1988 also shows that that any scheme whose plot passes through the second quadrant, here we have second quadrant, may produce unphysical oscillations which may occur to some extent with quick under strong convective conditions, since as one can see, the quick scheme passes through the second quadrant, right? Additionally, the schemes which pass through the fourth quadrant, here is the fourth quadrant, are artificially diffusive. Thus, to avoid both the unphysical oscillations and the artificial diffusiveness, the schemes must pass through the origin O. Further, the schemes passing above the point P are oscillatory in two-dimensional problems, which is the case for the second order upwind scheme and to some extent for the quick scheme, right? This explains largely why it is necessary to apply limiters to the predicted phase values when we use the second order upwind scheme. Okay, similarly, passing below P, below the point P here, gives artificially diffusive numerical results, so the schemes must pass through the point P either. Okay, thus the numerical schemes to be accurate and monotonic. For the normalized adjacent upstream node values from 0 to 1, they should pass through O, P and Q with a slope of 0.75 at Q. Okay, the normalized variable diagram is extremely helpful in problems where we have to deal with strong convection, such as the modeling of free surface, where we need to acquire a sharp interface between the water and air. So the summary of what I talked about in this video, we learned that what a strong convection is. We also understood the concept of normalized variable diagram. We learned that how different upwind schemes evaluate the convected control volume phase value, and finally, by utilizing the normalized variable diagram, we learned about the performance of each upwind scheme under strong convective condition. Okay, this is the end of this video. I hope you found this video useful. Please let me know what you think about this video by leaving a comment in the comment section. Thank you for watching the video, and for further upcoming videos, please subscribe to this channel.